Continue with the idea of the conservation of momentum. Let's go on to problem number 24. Problem number 24 states, suppose a clay model of a koala bear has a mass of 0.200 kilograms and slides on ice at a speed of 0.750 meters per second. Just fill this in here. And it runs into another clay model, which is initially motionless. So the second one has no velocity. Let's put ones in here for the koala bear. And because they're made of clay, it has a mass, by the way, of 0.350 kilograms. And because they're made of clay, they stick together. And it asks, what is their final velocity? Again, basically you start out with the first situation where you have two koala bear or two objects. One's flying in this direction, and the second one is just sitting there. So this is situation one and has its momentum. And then after they collide, they're stuck together. And now they're traveling at a different velocity. Now the mass of this is essentially going to be the sum of the two masses. So what you have is that m1 v1 plus m2 v2 is going to equal m1 plus m2 times v. Now it's easier because this is 0, so we can eliminate this. So we have 0.2 times 0.750 equals 0.2 plus 0.35 is 0.55 times v. So v is going to be these two multiplied together, then divided by this. And that's going to equal 0.27 meters per second. And I just assumed that this was positive, and then this is 0, so you don't have to worry about that. So the final velocity is also positive, meaning it's from left to right. Number 25 is similar. It says, consider the following question. A car is moving at 10 meters per second. So let's write down that. We know 10 meters per second. Crashes into a tree and stops in 0.26 seconds. Calculate the force on the seat exerted on it. And this is actually the first part of a previous problem we just did. The mass of the driver was 70. And so we had Ft is equal to mv. And F then is going to equal to 70 times 10 divided by 0.26. And so, lo and behold, the answer doesn't change from our previous problem. It's still 2,700. Now, it said, would the answer of this question be different if the car with the 70 kilogram passenger collided with a car that has a mass equal to and is traveling in the opposite direction at the same speed? The answer is essentially no, because the effect would be for this car to come to a stop just like it did. As long as you assume the time is the same, the answer would be no, because the car would come to a stop in the same way, even though it would be coming to a stop for a different reason. If the masses of the two cars are the same and they're traveling in opposite directions at the same rate, then the first car having the passenger would stop in the same amount of time with the same force, and everything would be the same. And so the answer would be no. Now, number 30 is where things start getting a little more exciting. And what we start talking about with number 30 is something called elastic collisions in two dimensions. Elastic collisions state the following. If something is called elastic, what that means is that the momentum is conserved and the kinetic energy is conserved. So the momentum of the collision is conserved and the kinetic energy of the collision is conserved. Now, normally most collisions are non-elastic, which means that the kinetic energy is not conserved. It could either be lost or, actually in some cases, it could gain. There could be a gain of kinetic energy. But the point being is that in both of these situations, the momentum and the kinetic energy is conserved. So let's look at a prop. Now, because we're looking at two different forces, two different things, the mathematics becomes much more complicated. And you'll see that in this first problem we're doing. So it says a 70 kilogram ice hockey goalie, so let's give him the moniker M1. He's 70 kilograms. And he is essentially at rest. So V1 is equal to 0. And he catches a puck, we'll call that M2, that's 0.15 kilograms. That's slapped at him at a velocity of 30. So V2 is 35.0 meters per second. And the goalie and the puck have an elastic collision, which means it hits his glove and then bounces out, okay, in the opposite direction. And the puck reflects back in the direction from which it came. Okay, so you have a goalie and a puck. Before their collision, the goalie's sitting there, the puck comes in like this. After, the goalie will be moving in this direction at a certain velocity. We'll call that V1 prime. And the puck will be moving in this direction at a, well, I should write it smaller since I wrote it smaller in the last one. It will be moving in this direction. We'll call that V2 prime. Now, according to the rules, basically the question is, what would be their final velocities in this case? So V1 prime and V2 prime are the two unknowns. And there are two unknowns, okay? If there are two unknowns, you have to have two equations. So first one is based on the conservation of linear momentum in one dimension. So M1 V1 plus M2 V2 has to equal M1 V1 prime plus M2 V2 prime. So M1 V1 is 0 because V1 is 0. So what that says is that 0.150 times 35.0 has to equal 70 times whatever V1 prime is plus 0.150 times whatever V2 prime is. Those are the two unknowns. So that's the first equation, and that takes this into account. The second one says that the kinetic energy of the goalie plus the kinetic energy of the puck before they collide has to equal the kinetic energy after they collide of the goalie plus the kinetic energy of the puck after they collide. And so you have, again, this is 0, so you have 1/2 times 0.150 times 35 squared equals 1/2 times 70 times V1 squared, prime squared, plus 1/2 M2, which is 0.15 times V2 prime squared. So now you have two equations and two unknowns. But I'll tell you that having done this math, because there's squares in here, makes it quite a bit harder And so basically, I'll let you guys work on this math part because, you know, your math skills might be superior to mine. But there are various ways you can do this. You can solve for V1 prime on this side and then put it in here, or vice versa. But I will tell you that V1 prime is equal to minus 34.9 meters per second. You can see that it's going in the opposite direction, so it's going to be minus, and that V2 prime is equal to 0.150 meters per second. And those are the answers. This is in the positive direction, so the goalie ends up, actually I drew the picture opposite is what it ends up. And so this is how things end up. This is actually V2 prime and this is V1. Sorry, I got the answers backwards. So I'm not going to waste a lot of time on this video working through the math here, but understand that what you have to do is take one of these and solve for one of the two variables and then substitute into the other. You have two equations, this one and this one, and you just have to work on it till you get that done. Not an easy math problem, I will admit. Let's do one more on this video. And we're going to do number 33. Number 33. And in number 33, we're going into inelastic collisions. Now, inelastic collisions, the momentum is conserved between the before and after collision, but the kinetic energy is not. There's kinetic energy that is lost in some way. Now, it says using the mass and speed data from example 8.1, assuming that the football player catches the ball with his feet off the ground with both of them moving horizontally, calculate. And so I went back to example 8.1, and what you have is a football player whose mass is 110 kilos, and his velocity is 8.00 meters per second. And the ball has a mass of 0.410 kilograms, and its velocity was 25.0 meters per second. Now, the first part of this problem, it tells you to assume that both are traveling in the same direction. So it says, calculate the final velocity if the ball and the player are going in the same direction. Now, he catches it, so you end up with the mass being the sum of these two, okay? So M1 V1 plus M2 V2 is going to equal M1 plus M2 times the new velocity. So that means that 110 times 8 plus 0.41 times 25 divided by those added together, 110.41, is going to equal the new velocity, and that new velocity is going to be 8.06 meters per second. Now, I'm going to skip down, or no, the next part of the problem, it says calculate the loss of kinetic energy. So you start out the before collision, the kinetic energy of the player is here, and the kinetic energy of the ball is m2v2 squared, and that's going to give you the kinetic energy of the two. If you do that math, you get 3,520 plus 128.15, which is going to equal approximately 3,650 joules of kinetic energy. Now, after he catches the ball, it's going to be m1 plus m2 times this new velocity squared. So that's going to be 1/2 times 110.41 times 8.06 squared. And the new kinetic energy is now 3590. And if you subtract these two, you see that we've lost 60 joules of energy. You started with this amount of energy, and then the final you use this, so the difference is 60 joules of energy. Now it says to do the same calculation, but assume that the two objects are flying in opposite directions. So if you do this first part, basically you're substituting 110 times 8, and then this velocity is going to be minus, so we're subtracting 0.41 times 25 over 110.41. And if you do that, the new velocity is 7.88 meters per second. Now, the before changes as well, does not change. And that's because when you square a negative velocity, it becomes positive. So that the before remain kinetic energy before remains the same at 3650. In other words, when we substitute a negative 25 in this top equation here, when you square that, it becomes positive. So this number doesn't change, even though the velocity is in the opposite direction. And so the energy before the player catches it is the same. However, obviously after is not the same, and you end up with 1/2 times 110.41 times now 7.88 squared, and that's going to give you 3420 joules. And you put 3420 and subtract that from that, and you end up with 230 joules lost. Now it says for you to speculate, might the loss of kinetic energy related to how much it hurts when you catch the pass? Certainly, that's one thing you could speculate, is this increased loss of energy goes into the hands of the receiver, and it's more energy if it's going right at you as opposed to if it's going in the same direction, and so you feel it more when you catch it like that.